Today, I'm revealing my most ambitious project, yet an AI robot that actually learns by itself. That's right, no manual, reprogramming, no pre-recorded patterns. It watches, tests, fails, and learns from experience just like a human or an animal would. By the end of this video, you'll see how I built it from scratch: hardware, coding, AI model, sensors, and all, and I'll show you a live demo of the robot learning in real time. Make sure to hit like, subscribe, and turn on notifications because this is just the beginning of our robotics journey. Section 1. The concept. Narration. So, what does it mean when we say an AI robot that learns by itself? Traditional robots follow predefined instructions. If obstacle, turn left, but a self-learning robot uses a concept called reinforcement learning, a form of machine learning where the robot learns by trial and error. It performs an action, checks the result, and adjusts its behavior to improve the outcome next time. This is the same principle behind how AlphaGo, ChatGPT's reasoning MEDs, or even autonomous cars learn to make decisions. So, my goal was simple: build a small, low-cost robot that can move, sense its environment, and gradually learn the best way to navigate without me telling it exactly how. Section 2. The hardware, build, visual, table with robot, parts, tools, and wiring. Let's start with the hardware. Core components. Microcontroller S32 because it has Wi-Fi, Bluetooth, and a decent processor for all edge tasks. Motor driver L298N, dual H bridge. Motors, 2 DC geared motors with rubber wheels. Power, 7.4 volts Li-don't. Battery pack. Sensors, ultrasonic distance sensor HC044, obstacle detection, infrared sensor pair 4, edge detection. MPU6050 gyroscope plus, accelerometer 4, motion stability, camera, OV264 module, for basic vision tasks. Chassis, 3D printed, body with modular slots. AL processing unit, since ESP32 alone can't handle deep learning training efficiently, I paired it with a Raspberry Pi for acting as the robot's brain. The Pi handles all the AL inference, model, updates, and reinforcement learning algorithms, while ESP32 executes the motor control in real time. Key feature: I used modular connections, meaning I can swap out sensors or boards easily to upgrade later. Section 3. Software and coding, visual, code editor, screen plus terminal logs. This is where the real magic happens. I designed the software stack in 3 layers. 1. Low-level control firmware, written in Arduino IDE for ESP32, handles real-time motor, commands and sensor, data collection. 2. AL communication layer, runs over MAC protocol between ESP32 and Raspberry Pi, allows the AL model to send movement, decisions and receive sensor feedback. 3. Reinforcement learning model, implemented in Python, using TensorFlow Lite and NumPy. Reward function is based on distance traveled without collision. Over time, the model adjusts motor speeds and turn angles to maximize reward. Here's a simplified pseudocode snippet. Python copy code for episode in range 1000. State equals get sensor, data, action equals model. Predict state, reward equals get reward, action, model. Update state, action, reward. After about 15-20 episodes, the robot starts moving more intelligently, avoiding obstacles instead of bumping into them. Learning features, self-tuning parameters, the model adjusts its learning rate, dynamic have, memory buffer, stores past 100 states and outcomes to avoid repeating mistakes. Real-time plotting, I added a live dashboard that shows accuracy and average reward increase. Section 4. The learning demo. Visual, robot on a test track, camera, following. Here comes the most exciting part, the live learning test. Test 1. At first, the robot is clueless. It spins randomly, bumps into walls, and stops often. Reward graph is almost flat. Test 5. Now it's starting to make sense. It slows near walls, takes wider turns, and starts avoiding dead ends. Test 10. It's actually learning. The robot can now cross the room with fewer than 2 collisions. The average reward score has increased by 65% since the start. This means the reinforcement learning algorithm is working. The robot is improving its decisions using experience. Cool feature. When the robot performs well, it remembers that action sequence and saves it as a success pattern. If power goes off, it reloads the last saved model and continues from there, just like a human learning session. Section 5. Smart Vision upgrade. After the navigation model stabilized, I added computer vision capability. Using the camera and OpenCV, I trained it to detect colored objects, red, blue, green, and follow only a specific one. For example, a red ball. So now, the robot doesn't just avoid obstacles, it can also identify and follow a target. Here's the logic. Capture frame, detect color blob, calculate center of mass, turn motors toward that direction. This small addition transforms it from a random explorer to a goal-driven AI agent, a key concept in robotics research. Section 6. Communication and cloud sync. To make it smarter, over time, I added a Wi-Fi cloud sync system. The robot uploads its learning data, sensor readings, rewards, model weights to a Firebase cloud every 30 minutes. That means I can train one robot, upload the weights, and deploy the same brain into another robot instantly. This is like distributed AI training. Multiple robots can learn separately and share experiences to accelerate improvement collectively. Section 7. Real-world applications. Now, you might ask, why build this? What's the point? Here are a few real-world applications of self-learning robots: autonomous delivery bots that adapt to new routes, warehouse automation systems that learn object placement, elderly care robots that learn a person's daily routine. High research on how physical agents learn in dynamic environments. STEM education helping students understand how AI learns from data. Even though this project is small, it represents the foundation of adaptive robotics, robots that don't just execute code, but evolve over time. Section 8. Cost, challenges, and lessons. Let's talk about some practical details. Project cost, approximate. Component and price: S32, $10, Raspberry Pi 4, $60, motors plus driver, $15, sensors, $20, camera, $10, battery plus chassis, $25. Total equals $140. Not bad for a self-learning robot that can train itself. Challenges faced: 1. Power management. Pi plus motors equals high current draw. Needed separate regulators. 2. Model convergence. At first, the AI oscillated between random behaviors. Fine-tuning reward functions fixed it. 3. Sensor noise. Ultrasonic sensor misreadings caused random turns. Solved with Kalman filtering. 4. Data logging needed. Efficient way to sync data without slowing robot down. Lessons learned. AI plus hardware is not just coding, its system design. Reward design is everything in reinforcement learning. Edge AI can do wonders with lightweight models if optimized right. Section 9. Future upgrades. The next version, HPHEM Bot 2.0, will include LiDAR scanning for full 3D mapping, voice recognition for verbal commands, self-charging dock integration, neural network updates over Wi-Fi. These upgrades will make it even more autonomous, like a mini version of a self-learning research robot used in labs. Section 10. Closing and call to action. Visual. Robot moving smoothly, turning around obstacles. And that's it myself. Learning AI robot. Built from scratch, coded to think, and trained to adapt. If you enjoyed this deep tech build, hit like, subscribe, and comment below what feature you want me to add next. Maybe a robotic arm, face recognition, or voice-based control. Thanks for watching.